Hi everyone, today we'll be taking a look at total probability theorem and the Bayes theorem. Okay, so let's start off by understanding what the total probability theorem is with the help of an example question. Okay, so in this question we're told that box 1 contains 3 red and 7 blue balls. Box 2 contains 6 red and 4 blue, okay? And 4 blue. A dice is rolled. If the outcome of is a multiple of 3, a ball is drawn from box 1. Otherwise, a ball is drawn from box 2. What is the probability that the ball drawn is red in color? Okay, so we have two situations. So normally, whenever you face such situational or conditional based questions, right, I would highly recommend that you start drawing a tree diagram. Okay, so in this situation, we have two options, right? So we decide whether to pick a ball from box 1 or box 2 based on whether we get a multiple of 3 or not. So first of all, let's look at what are the multiples of 3. Well, that's just 3 and 6 because our sample space is 1, 2, 3, 4, 5, and 6, right? Because when you roll a dice, you have 6 different options. Out of them, only 3 and 6 are multiples of 3. Right? So let's say we roll the dice. I'm going to draw my dice here like this, right? 1, 2, 3. Okay, so I'm going to have two possible events, event 1 and event 2. Okay, so event 1 is, let's say you do get you roll a multiple of 3. So if you roll a multiple of 3, you have two options. You get to pick from box 1, right? So box 1 will have 3 red and 7 blue. Similarly, if you choose non-multiples of 3, then you have the option of box 2, which is 6 red and 4 blue, right here, like this. Okay. All right, so now, and then we choose the red ball, right? So the red ball would kind of, in this, essentially be probability of red given that it's E1, and probability of red given that event 2 takes place, right? We're working under the condition that event 2 takes place, right? So how do we figure this out? Well, let's break it down, okay? So what is the probability that event 1 occurs? Event 1 is the probability that a multiple of 3 is obtained. Well, there are two options, right? 2 out of 6. So you can say that it's 1/3 and this is 2/3. Similarly, what is the probability that we get a red colored ball? Well, that's 3 out of 10 right here. And it's 6 out of 10 right here. Okay, so now, well, to figure it out exactly, since these are also independent events, right? Kind of sort on the lines of those independent events, if you remember from the previous video. What we do is, now to find the total probability of red, we just multiply 1/3 with 3/10 and 2/3 with 6/10, like this. What are we left with? What will we have? 3/30 plus 12/30, which is 15/30, which is a half. So the probability that a red colored ball is drawn is 50%. Okay, so this was something that we just did intuitively. Now let's see if we were to use sort of the formulas that we have learned, right? So the probability of red would have two options, right? That event 1 and red take place, and probability that event 2 and red is selected, like this. Now, if you remember conditional probability theorem, I'm just going to rearrange that and fit it according to my this situation right here. So I'm going to have probability of event, it's going to be event, probability of red given event 1 takes place times event 1, like this, and probability that red is selected given event 2 is taken into consideration multiplied by event 2. And then you know, we can just take the same thing. So 1/3 times 3/10. So, or I can say 3/10 times 1/3. Similarly, we're going to have 6/10 times 2/3, like this, like so. And then again, we get a half. Now, why am I multiplying? Well, remember, the probability of E1 is not going to change whether event 1 or event 2 is taken into consideration. They're independent events. Both of them, me selecting a red ball is not dependent on me selecting a red ball from bag 1 or bag 2 is not dependent on whether I roll a dice, right? It's not going to influence whether I roll a multiple of 3 or not, right? Regardless, like the probability of picking a red ball from either of the bags is going to be independent of what number I roll on my dice, right? So going back here, let me just change the color, right? So I hope this tree diagram kind of made sense, because this arrow is now going to have a conditional probability here, because now I'm saying probability of red is selected given that E1 takes place. I just won't do probability of E1, right? Because this arrow right here in purple now, which was originally green, is dependent on whether event 1 takes place or event 2 takes place. So that's why we're gonna bring in conditional probability here, right? If this feels a little tricky to you, what I do recommend is to open your textbooks, whether it's the Oxford one or the Pearson one, or any other ones that you have, and solve the simple tree diagram questions, or the questions which require you to draw a tree diagram, right? Once you draw and chart out the possible probabilities and the permutations, it's really easy to break it down and find what's needed. Okay, so now that we have done this, let's look at another question very similar to what we previously did. Okay, so we're told that box 1 contains 3 red, 7 blue balls. Box 2 contains 6 red and 4 blue balls. A ball is randomly selected from box 1 and placed in box 2. Now a ball is drawn from box 2. So what is the probability that a ball is drawn, the ball drawn is red in color? Again, let's break it down, right? We can have 2 events going here as well, right? Like this. We can have event 1 and event 2. Well, I'm going to call event 1 such that a red color ball is chosen, okay? If a red color ball is chosen from box 1, okay, the probability is 3/10. Why? Because there are 3 and total balls are 10, so simple as that. Then, other probability is that a blue ball is taken, so that's going to be 7/10. Okay. Now we have to find out the possibilities, right? So we have in box 2, we have 6 red and 4 blue balls. Now, assuming that event 1 happens, then we're going to be left with, let me change the color. We're going to be left with 7 red and 4 blue. And if event 2 takes place, we're going to have 6 red, 5 blue. That's it. So this is going to be probability of red, right? Probability of blue, kind of like that, or in red inverse. This is going to be probability of red given event 1 takes place, and probability of red given event 2 takes place. Okay, very similar to the first question, right? And now, well, what's the probability of selecting red? Well, that's going to be 7 out of 11, and this is going to be 6 out of 11, right? That's what it's going to be. So let's take it to the next page. Again, it's going to be the same idea. I'm going to have probability of red given E1 times probability of E1 plus probability of red given E2, which is selecting blue from the first box, and I'm gonna have probability of event 2. So what is the first conditional probability of event 1? That's gonna be 7 by 11, 7 by 11, and it's gonna be 6 by 11, and this was I believe, 3 by 10 and 7 by 10, right? Okay, so 3 by 10 and 7 by 10. So what are we left with? Well, we have 21 by 110 plus 42 by 110, and we get 63 by 110. Right, and that's my final answer. Okay. So I hope that made sense. Again, it's a very similar question to what we previously did, just a little bit of changing here and there. First part was again finding the general probability, and the second part was the conditional part. Why? Because it was dependent on what happened on the previous. Remember, conditional and independent are two completely different things. Don't mix them up, right? It's very easy to think that, oh, if it's conditional, it's not independent. No, it's still independent, because remember, this probability is independent of this, right? Yes, it's kind of like, yes, obviously, uh, it is, whether event one or event two takes place, that's going to determine how many red balls and how many blue balls are there. But this selection of, let's say, first you and your friend, put up two boxes of, these many red and blue balls, and then you guys independently select these, right? When you guys are doing the second step of this experiment or selection, right? This is not going to be influenced by what happened previously, right? That's why it's still independent to an extent. You can think of it that way, right? Okay, so now that gets me to the main aspect of total probability theorem. Okay, so what this says is if an event A can occur with one of the n mutually exclusive and exhaustive events B1, B2, all the way to Bn n number of times, then the probabilities probability of A given that B2 happens or B1 happens, I mean you can take anything, are known. Then, well, we can say that probability of A is essentially the sum of probability of starting I equal to 1 all the way to n. We can say it as probability of A times BI times probability of BI, like this. Okay, so we can say probability of event A occurring with the first B event times the probability of the B event occurring in general, right? So this goes on. Now this is kind of like, probability of A given B1 happens times probability of B1 plus probability of A given B2 happens times probability of B2, and so on and so forth till the nth possible event. Okay. Now if you're studying this for the first time, you're gonna be a little confused, right? It might not make the most intuitive sense. That's why tree diagrams really help, right? That's why I wanted to show how we solve the questions just with the help of tree diagrams. We wouldn't have really needed these formulas because we knew what the conditional probabilities already were, right? The second part of the tree diagram were already conditional probabilities, and we could have just multiplied them because we know they're independent events, in the sense that I explained previously before. So this formula, to an extent, was not at all needed, but since this is part of what the math is and part of what the content teaches you, I thought that we explicitly state what total probability theorem. It's just asking the total probability of one event occurring. You can reverse it as well, total probability of B, and then you just swap the A's and B's together. Nonetheless, let's look towards now Bayes' theorem. Okay. So Bayes' theorem is very similar to what total probability theorem states. Okay, so the Bayes' theorem says that let's say we have an event BI, a specific event of B. Let's say rolling a dice or picking a red colored ball out of a box, right? Given that some event A previously takes place. So this can actually be, denoted or written as probability of A given that BI occurs times probability of B. Okay, and this can be, or sorry, BI, and this can be, it's the probability of, and the total probability below would be is the summation, or the, summing up all of the events that can take place from I1 to N, with the same scenario here, like this, probability of BI. Now, this is actually just a very complicated version of, probability of BI and, or let me write it in, a little neater, a little bit more clean fashion. Okay, so this can be written as probability of BI and A occurring, total probability of A. So let me change the color. So this blue arrow right here correlates to the top part, and this red arrow here correlates to the bottom part. Okay, if you understand this, this is like the total probability theorem, the one in the red arrow, right? And the blue arrow, it's what conditional probability is about, just reversing the conditional probability. It's like taking, probability of A given B, which is probability of A and B by probability of B, and then using probability of B and A, probability of A and B by probability of A, and then just replacing this part with this entire segment. Okay, so this would come out to be probability of A given B is equal to probability of B given A times probability of A by probability of B. This is what it's essentially saying, right? In a nutshell, this is like for one specific event, but let's say there are multiple. It's an exhaustive event with multiple possibilities. This is why we have the summation and the subscript of the I taking place, right? So why the conditionals? Why so many conditional probabilities? Well, when we drew the tree diagrams, the second branch were conditional based off of the first event taking place. That's why we have these conditional branches. Okay, so now that we've taken a look at Bayes' theorem, let's solve a question using what we have learned. Okay, so I'm going to solve this question both ways using the Bayes' theorem formulas, and what I'll do is I will also show how we can do it using a tree diagram. Okay, so let's use the Bayes' theorem this time. It's a little bit more mechanical, but let's understand how we're using that as well. Okay, so we're told that a pack of cards is counted with face down. It is found that a card is missing. Now, one card is drawn and is found to be red. So find the probability that the missing card is also red. Okay? So what we're told to find is the probability that the missing card is red. Okay? But this part is a little different. Okay? So let's denote some variables. Let's say R is red card being selected. Okay? Red card being missing. Okay? And B is for black card going missing. Okay, black card missing. And I'm gonna say D for drawn. Okay, red card being drawn. Red card drawn. Okay, so what we're told to find is find the probability that the missing card is red, or the card drawn is red, given that the red card is missing. So what we're told is to find the probability that the red card is missing given that the red card is drawn. Okay, so we can expand this as saying probability of red card being drawn, and I'm not gonna write the original formula. I'm just gonna write the reverse one. So I'm gonna write the other conditional one times probability of red card. Okay, like this. So we know that probability of red is half, and probability of black is also half. Why? Think about it. If there are 52 cards in a deck and one of them were to go missing, well, there are 26 red, 26 black. There's an equal probability of both cards going missing, right? So we have this part sorted. Now let's go to the remaining aspects of this expression or equation. Well, we're told that, well, you can use that, what we've done previously to figure this part out. What we can do is probability of D given R times probability of R plus probability of a red card being drawn given black card is missing times probability of black card. Okay? we have this as well. Now we have to find the last part of the puzzle, which is this in green, right? Well, think about it. Now, what is the probability that a red card will be drawn given that a red card is missing? Well, we know if a red card is missing, right? Probability that a red card is missing, there are only 51 total cards. And out of the 26 red cards, one card is already missing, so that's 25, like this. Similarly, if we had probability of red card being drawn given that black card is missing, that would be 26 by 51, right? Think about it. Pause the video, give it a thought, okay? So now that we have all the information in place, well, we can just sub it in, right? Probability of red card being drawn given that a red card is missing, given that a red card is drawn, and we can just plug in all the information that we have. Well, this is a half, this is a half, this is 26 by 51, this is 25 by 51, and this part d-r, this part is the same as the one on top, so I'm going to write 25 by 51 times a half, 25 by 51 times a half, plus 26 by 51 times a half. Well, the halves can cancel out, 51s can cancel out, and what I'm left with is my final answer is going to be 25 by 51. Okay, this is my final answer. So probability that the red card is missing given that the red card is drawn from the remaining 51 cards is 25 by 51. Now this answer, you could have gotten it accidentally as well, because the numbers are really simple to work with, and there are only two possibilities, either red, either black, right? Now let's draw a tree diagram in this situation. Let's see how we would solve it. So we have two options again. The first option is the red card going missing. The second option is the black card going missing, right? Each of their probabilities is 50-50, right? Each of their probabilities is 50-50 because we have 52 cards, 26 red, 26 black. You can randomly pick one, and the possibility of selecting either red or black is 50-50, right? So now, second part would be, again, to extend this arrow, right? And would be to select probability of, select drawing a red card given that a black goes missing and a red goes missing. Well, that would, again, as we thought about it, right? There are 51 cards and red is already missing, so there should be 25 remaining. Similarly here, there would be 26 by 51. And if we have to find probability of D, right? So probability of D would just be probability of D by RM, given RM, times R is missing, plus probability of selecting D given that black goes missing, times probability of black going missing, right? Numbers are really easy to work with, that's why. So I hope the concept is, a lot more clear now. So 25 by 51 times, again, this is the total addition theorem that we previously looked at, right? We're incorporating that and Bayes' theorem together. And then we would have 26 by 51 plus another half, like this, right? Like that. So, once you can solve it, you get the same answer as 25 by 51, right? Okay, so with this, we wrap up probability and Bayes' theorem, and I'll see you in the next video. Bye-bye.